Okay. So we're going to start with a simple scenario. Part A of the lab has a post-lab question that has a scenario kind of like this. And what they say is that you took dialysis tubing, and in the dialysis tubing, you put different concentrations of sugar. And then you put each of these dialysis tubes into pure water. And you left it there, let's say, for 30 minutes, and then you calculated the percent change in mass. So just kind of visualize, this is what they're saying they did. They took these different dialysis tubings. We're also pretending in this scenario like the sugar solution cannot pass through, but only the water can. So we're pretending like only water can pass through the membrane. All right, so for starters, if I put a tube of water into water, would you expect that to gain weight, lose weight, or stay the same?
Stay the same.
Correct. That should stay the same. That's isotonic, right? That's our textbook definition of isotonic. So if I was going to graph this, most likely the data I would get would be that there would be no percent change. So this is the contents of my bag, the molarity in the bag, and it probably would not gain or lose any weight. In a perfect world. In real life, you might see some tiny bit of change. All right, scenario 2. I now take a 0.2 molar bag and I put it into pure water. Remember, pure water is 0 molar. So this bag would be hypertonic, right? Hyper has more solute than the pure water. Should that bag gain weight, lose weight?
Gain.
That bag should gain weight. In fact, all of these bags should gain weight. But here's the important thing that I want you to understand, and I don't know that we've ever really talked about this. What you would find is that the steeper the concentration, in other words, the more difference there is on the two sides of the membrane, the more weight the bags would gain. So you would probably get some kind of data that looks something like this. Might not be a perfect line. And again, the reason why is because if you have pure water on one side and you have an increasing amount of solute on the other side, the more solute there is, that means there's less space for water. So water is going to tend to be going towards this side to dilute the solute, and there's not going to be a lot of water going the other way because there's less water over here to begin with, and the chances of a water molecule hitting from this side are much lower because there's all this solute in the way. So the steeper, they call it having a steeper concentration gradient, the more weight the bags would gain. So more hypertonic bag, more weight gain. So does anybody have any questions about that scenario? Okay, so that's post-lab of part 1 is going to ask you to make a graph kind of similar to this, and they're going to give you some data. And so I just wanted you to kind of see a visual so you had an idea of what they're telling you they did. Now, let's switch it up. So now let's say instead of putting the contents in the bag, I'm putting my sugar solutions in the beaker. So this is the opposite. I'm putting a bag of pure water into each of these solutions. So pure water into pure water, just like last time, we would expect no change. What about pure water put into 0.2? Do you think this bag would gain weight or lose weight?
Lose.
Right, so we would expect this bag is going to lose because now the solutions out here are hypertonic, and my bag in all these solutions, other than the pure water, my bag is hypo. It has less solute than the solutions outside. And just like in the scenario before, the bigger the concentration difference, so my pure water put into 0.2 is going to lose a little bit of weight. In 0.4, it's going to lose more. In 0.6, it's going to lose more. And I would get a graph that generally would go down. It may, I'm just making up numbers, so understand the line might not look exactly like this. But they should all lose weight, which is why my graph is upside down, why my percent changes are all negative. Because all my bags, other than pure water, in this scenario should lose weight. So any questions about this scenario?
I have a quick question.
Yes.
Are we going to be given the percent change, or do we have to figure it out in this scenario?
Good question. For purposes of the lab, part 1, they gave you the percent changes. And on the test, for anything that you're graphing, I'm giving you the percent changes. I do have one test question, and it's just one question, where I give you an initial and a final, and I ask you to calculate percent change. But you're not going to have to calculate and then graph.
Okay, thank you.
You're welcome. Okay, so scenario C. Now I have a bag of 0.5 molar sucrose, and I'm going to put it into 3 solutions. And I think this will help a lot with part C of the lab, or part 3 of the lab. So we already said that if we put a bag of sucrose into water, my bag should my bag should gain weight, right? My bag, in this case, my pure water would be hypo, my bag would be hyper, and my bag should gain weight, right? Does that make sense to everybody? More sucrose in the bag, lower solute outside the bag. So in my pure water, my bag should gain weight. So I'm just going to put, this is the molarity, just to clarify, this is the beaker molarity. I didn't put it here, not the bag molarity. So this is my beaker molarity. And so in 0 molar pure water, my bag would gain some amount of weight. Again, I'm just going to put my dot at 6. I'm just making up numbers. All right, what if I put easy one for everybody? Put 0.5 into 0.5. What should we see? Right, it should stay the same, right? Because it's isotonic. So this is isotonic. So we should see it right here, right on the x-axis with no percent change because it's isotonic. And then obviously that means that if I put my 0.5 into my 1.0, now my beaker is hyper, my bag would be hypo, and now my bag would lose weight. And I would get something that looks like this. It may not end up being, again, a perfect straight line. And the important thing is right here where it crosses the x-axis, that is where it would be isotonic to the solution, right? Because I wouldn't expect it to gain or lose if it's the same concentration. Okay, so here's what you did in the lab. You basically did this in part 3 with the potatoes, except it would be like this. We didn't know what the potatoes were, but we put the potatoes into a 0 and a 0.2 and a 0.4 and a 0.6. We put it into all these solutions and we collected data. Now watch. This will tell me if you actually understand this or not. So let's just say I have my bag and I don't know what the molarity of the bag inside the bag is, but I graph it and I get this. What would you estimate to be the molarity of the solution in the bag?
0.3.
Good. So somebody said 0.3. Exactly. How are you going to know? It's going to be wherever it crosses the x-axis, because we just said from the previous problem that wherever it crosses the x would be where we would predict it would be isotonic. It wouldn't gain weight or lose weight. And that's what you're doing with the potatoes. We put them in the different solutions. You're going to graph your data, and your answer to this is going to be C, the molarity inside the potatoes. So if we go take this and relate it to our formula. So if you were told it's 25 degrees Celsius, the solution was sucrose. We put them in sugar solution. We know what R is. We're converting our Celsius to 298. That's our Kelvin. Here's our formula. If you were asked, calculate the solute potential of the solution in this bag, the only information you don't have yet is C. And you'd get that from your graph. Wherever it crosses the x-axis, that's the molarity inside the actual bag. Or in our case, in the potatoes. So let me scroll back up to the graph from yesterday, and hopefully if you were left here yesterday going, I did not understand that last graph, it may make more sense. And I think I gave you, this is the graph I was saying, I think I gave you an incorrect number yesterday. So if you took a picture of my graph yesterday, I think I had like 0.2 something, that's not right. So here's my graph. I've labeled my x-axis molarity. There's my percent change. Where did I get these numbers from? Here. This is the data from our notes. So here were the potatoes in this is sample data, not our actual lab. Notice in this scenario, they gained weight in 0 and 0.2. And then in 0.4, they suddenly started losing weight. So I know somewhere between 0.2 and 0.4 would be isotonic, would be the actual molarity inside the potatoes. So what I did was I graphed it from my pure water to my 1.0, and to be honest, the only part of the graph that matters is here, where you think it crosses the x-axis. And my best estimate was 0.36 molar. Now, again, when you do this with the actual lab data, everybody's lines may be slightly different. That's fine. But if I put this on a test and somebody tells me that C is 0.8, I'm going to know they don't know what the heck they're doing. Because obviously, you can tell even from the table, it's got to be somewhere between 0.2 and 0.4 because you go from positive to negative there. So I know the molarity you estimate has to fall somewhere between those two numbers. And so that's how you, in the potato lab, your graph is going to look like this. Something like this. It's not going to necessarily cross at 0.36 because we're using different numbers. We're using the numbers from the lab. So before I go to the actual lab and show you guys the sample data and walk everybody through all the parts and what needs to be there, are there any questions on what I just went through today?